Hello everyone, my name is Nitya Mishra and today we are going to talk about the comparative analysis of CPU, GPU, NPU, LPU and TPU. Artificial intelligence is changing the entire computing industry. But behind every AI model, smartphone, game engine and chatbot, there's a different kind of processor working silently. CPUs, GPUs, NPUs, TPUs, and LPUs. Each one is designed differently. Each one solves a different problem. And today we will compare all five architectures in detail. Let's talk about the landscape of silicon. Modern computing no longer depends on one universal chip. Instead, different processors specialize in different workloads. The CPU is general purpose brain. GPU focuses on massive parallel computation. The NPUs bring AI directly to edge devices. The TPU accelerates tensor operation for cloud AI, and the LPU is optimized specifically for large scale language model inference. This shift from general purpose computing to specialized computing is one of the biggest changes in computer architecture. Let's start with the CPU, the central processing unit. The CPU is the foundation of modern computing. Unlike AI accelerators, the CPU is designed to do dif- everything reasonably well. Operating system, AI applications, web browser, databases, and compilers all rely heavily on CPU. So must be wondering about CPU's architecture and flow. CPUs work using sequential execution. Instruction move through stages like fetch, decode, execute, and write back. What makes CPUs special is their intelligence. They contain branch predictors, large cache hierarchy, out of order execution engines, and highly advanced control logic. Compared to GPUs, CPUs have far fewer cores, but each core is significantly more powerful and flexible. Let's talk about pros and cons of CPU. So, where does the computer shine? CPUs dominate sequential and decision-heavy tasks. They are flexible, software compatible, and excellent for operating system and complex logic. But compared to GPUs or TPUs, CPUs struggle with parallel AI workloads. A CPU might have 8 or 16 powerful cores, while a GPU can contain thousands of small parallel cores. That's why CPUs are the brain of the system but not the fastest AI engine. Now we move to the GPU, the graphics processing unit. Originally, GPUs were built for graphics rendering, but AI researchers discovered something important. The parallel math used for graphics is also perfect for neural networks. Let's move forward to GPU throughput machine. Unlike CPUs, GPUs sacrifice complex control logic to maximize throughput. Instead of a few strong cores, GPUs contain thousands of lightweight CUDA cores. This makes them incredibly efficient for matrix multiplication, deep learning simulation, and rendering. The GPU's biggest advantage over CPU is parallelism. While CPUs process tasks one after another, GPUs process thousands simultaneously. We have ecosystem advantages such as CUDA, PyTorch, TensorFlow, and many more. They are best for high bandwidth memory integration. Now let's move to pros and cons of GPU. GPUs currently dominate AI training. Why? Because neural networks are basically giant matrix operation, exactly what GPUs are optimized for. The CUDA ecosystem also gives NVIDIA a massive advantage, but GPUs come with major drawbacks: high power consumption, high heat generation, extremely high cost. Compared to NPUs or LPUs, GPUs are far less powerful and far less power efficient. Next comes the NPU, the Neural Processing Unit. This architecture focuses on a completely different problem: running AI directly on devices. NPU on device intelligence. NPUs are custom built to accelerate neural network layers, convolution, pooling, attention. Unlike general chips that prioritize performance per watt, they are efficient for tasks like face unlock, camera enhancement, speech recognition, and real time translation. Compared to GPUs, NPUs come dramatically less power. That's why your phone can run AI continuously without overheating. Let's talk about pros and cons of NPU. The NPU's biggest strength is performance per watt. It enables local AI processing, better privacy, and lower latency. But NPUs are highly specialized. They are designed mainly for inference, not large scale training. Compared to GPUs and TPUs, NPUs cannot handle giant performance training workloads. Now we reach the TPU, the Tensor Processing Unit. Google created TPUs specifically to accelerate machine learning at massive scale. TPU matrix optimization. The TPU is designed around one core idea: multi matrix multiplication. Its systolic array architecture allows data to flow continuously through computation units. Compared to GPUs, TPUs reduce memory bottlenecks more aggressively. That makes TPUs extremely efficient for transformer training. This is why Google uses TPU pods for models like Gemini and Farm. Let's talk about the pros and cons of TPU. TPUs provide incredible AI throughput. For large scale training, they can outperform GPUs in efficiency and cost. But there is a trade off. Compared to GPUs, TPUs are less flexible. They work inside Google's ecosystem and are optimized heavily for tensor based workload. They have poor flexibility and not for inference. Now, let's talk about LPU instant response. LPUs are designed specifically for large language models. Unlike GPUs, which optimize AI workloads, LPUs focused almost entirely on inference latency. They use deterministic execution and SRAM-first architecture to reduce memory delays. This allows systems like Grok LPU to generate tokens extremely quickly. Let's talk about pros and cons of LPU. The LPU's biggest advantage is speed. Compared to GPUs, LPUs can generate significantly more tokens per second while consuming less power. They also avoid unpredictable scheduling delays. However, LPUs are highly specialized. They are excellent for LLM inference but not suitable for general purpose AI training. Now, if we are comparing something, we should take something in mm, remarks. Now, let's talk about throughput benchmark. This benchmark highlights the differences between architecture. CPUs provide flexibility but limited AI throughput. CPU dominate parallel training workload. TPUs optimize tensor efficiency for cloud scale AI. NPUs focus on efficient edge inference, and LPUs currently provide the best latency for real-time language generation. We have some comparative analysis between their throughput benchmark. Now, let's talk about compute optimization by domain. Each processor dominates a different market segment. CPUs remain essential for general computing. GPUs dominate AI research and training. NPUs power billions of mobile devices, and TPUs specialize in enterprise cloud AI. LPUs are emerging for ultra-fast conversational AI systems. Their market and inside are changing drastically. CPUs and GPUs still dominate computer market by dollar value. However, NPUs are growing fastest by unit volume, already shipping in every premium smartphone globally. LPU ASIC share is small but growing rapidly as real-time inference becomes a priority for consumer products and enterprise chatbot APIs. So, what you must be thinking of future of AI hardware and energy efficiency. The future of computing is becoming increasingly specialized. Instead of one universal processor, future systems will combine multiple accelerators together. We are already seeing AI specific ASICs, chiplet designs, 3D memory stacking, and photonic computing. We have some case study, some previous examples such as in 2015 we have CPU and GPU dominance, Intel Xeon and Nvidia K80 first wave of deep learning, all training done on GPU clusters, CPU for everything else. In 2020 we had TPU V3 and smartphone NPUs. Google TPU pod scale petaflops, Apple A14 neural engine launches, and ASIC era begins in earnest. In 2015, the latest and newest version, LPU latest ASIC, Grok LPU, and Apple M series purpose-built silicon delivers 24x TOPS watt over 2015 baseline. So When we compare all architecture together, a clear pattern appears. CPUs prioritize flexibility, GPU prioritizes throughput, TPUs prioritize tensor efficiency, NPUs prioritize power efficiency, and LPUs prioritize latency. Each architecture exists because no single chip can optimize everything simultaneously. How these are compared with each other on some comparative metrics are mentioned over here in this slide. So, which processor is best and how quantum and neuromorphic the frontier in computing works. Neuromorphic Intel Lahi 2 and IBM Northpole take inspiration from human brain event-driven, sparse, ultra-low power, billions of artificial neurons firing like synapses. Quantum processors. Quantum processor for optimization and simulation problems. Photonic computing for AI matrix operation at the speed of light. Still nascent but accelerating. The which processor is best? The answer depends entirely on workload. For general computing, CPU. For AI training, GPU or TPU. For mobile AI, we have NPU, and for real-time LLM we have LPU. The era of one universal processor is ending. Modern computing is now built around specialization. Different workloads require completely different architecture optimization. So stick to hardcore count CPUs unbeatable for branching logic, OS, and flexible workloads. GPUs remain the industry standard, mature CUDA ecosystem, high memory bandwidth. Google's TPU offer optimal ROI for transformer training at petaflop scale. LPUs are the emerging gold standards, 500 to 800 TOE per second at a fraction of GPU power. Integrated NPUs are essential for privacy, first AI, and battery constrained inference. So, different workloads require different architecture optimization. CPUs remain the foundation of computing. GPU transformed AI training. TPUs optimized cloud scale machine learning. NPUs brought AI directly to edge devices, and LPUs redefining real time language generation. So, thank you for watching this complete comparative analysis for CPUs, GPUs, NPUs, TPUs, and LPUs. Because to end with, I would like to summarize that the future is heterogeneous. No single chip rules all workloads. The best system combine CPU, GPU, NPU, TPU, and LPU. Thank you and have a nice day.